Hi there. Today we are going to be finishing up Chapter 5, covering 5.4, 5.5, 5.6, 5.7, and 5.8. All of these are introducing different integration techniques, and this is really just a handful of them. It turns out that there are a ton of integration techniques out there. If you took Math 400, you would experience a majority of them, 400 and 401. Here we're going to be introducing you to the most important ones. And to show why this is necessary, when we think about the antiderivatives, well, before we discussed how it's really difficult, but as long as we know our differentiation formulas, we should be in good shape. But there are some which just knowing our differentiation formulas isn't going to be enough for. For instance, the integral of the natural log of x dx. Well, we don't have a formula for that one. Same for integral of tangent. I mean, tangent is a core fundamental function, but we don't have a formula for the antiderivative of it. And so what we need some techniques to make it so that we can find the antiderivative of these functions. Even with that, though, there are going to be some functions which we are not going to be able to find the antiderivative of. One of the most important ones is e to the negative x squared. The function e to the negative x squared gives you the standard bell curve, which you see in statistics. However, we are unable to find the area under that curve, at least not on any specific interval very nicely. There is no set formula for it. And so this set of techniques that we're going to be covering today is basically going to be giving you a helping hand towards integration. And we'll be seeing lots and lots of different problems arise. And so let's jump into it. The first technique is the substitution method. The substitution method is really doing the chain rule backwards. And so if you remember the chain rule says that if you have a function inside of a function, and so in this case, u of x is a function which is inside of the function f. Well, in order to take the derivative of it, we would take the derivative of the outside function, so the derivative of f, and then you would multiply that by the derivative of the inside function. In order to do this backwards, well, if we integrate both sides, we would get that the integral of, the integral of the derivative of f of u of x would just be f of u of x plus c. But then the integral of f prime of u of x times u prime of x dx is what's going to give you that f of u of x plus c. And that becomes kind of a messy thing. If we ever have something that looks like this bit on the left, the integral of f prime of u of x times u prime of x dx, we can rewrite that as f of u of x plus c. Note, physicists write this in a way which makes it a little easier to see. If you have dy du times du dx, well, they would just cancel the dx's and the du's and be left with the integral of dy, which is just y plus c. But we don't like physicists because they make it much too easy. We want to make it very complicated like a good mathematician. But let me show you what this is doing with an example, because I think just seeing all of these letters flowing around, it's not going to make as much sense. And so let's try an example. Let's take the derivative d dx of, how about sine of x to the third power? Well, if we take the derivative of sine of x cubed, we know that we would do the cosine of x to the third, and then we would have to multiply it by the derivative of that inside part, the derivative of x cubed, which is 3x squared. Well, if we break this up, what we're saying is that this core function is our function f of x. And then this function is our u of x function. Well, then this bit, and so in this case, this would be u of x, and this would be f of u of x. Well, in this bit here, cosine of x cubed, that's really f prime. But it still has the u of x on the inside because the x cubed is still the x cubed. But then it's being multiplied by u prime of x. Where the integrals come from is if we took the integral of both sides, well, this side would give us the integral of f prime of u of x dx, or times u prime of x dx. And this side, the integral of a derivative is just going to give you your starting function, f of u of x plus c. Or if we wanted to see it written with our sines and cosines, this is just a fancy way of saying that the integral of cosine of x cubed times 3x squared dx is equal to sine of x cubed plus c. And I don't know if that made it easier to see or not, but we can start to see all of these different components and how they're all coming together. And so here we have a function inside of a function, and it's multiplied by the derivative of that interior function. That's really what's required for the substitution rule to be in place. And so we have to have a function inside of a function. And so in this case, u of x is within this function f prime. And the derivative of this interior function is then on the outside being multiplied. If that's ever the case, then we can integrate it using the substitution rule. Now, I have some guidelines on how to actually do this in practice. And let's read through those guidelines and then we'll go through some practice problems. And so to solve using the substitution method, the first thing you want to do is look at the different components of your integrand to identify what the core function is that you're dealing with. And maybe core function isn't as descriptive as I would want. What you want to be doing is you want to be looking for whatever function is a composition of functions. And so whatever function has another function inside of it. Choose u to be the expression which is inside of your core function, and then determine what du dx is. If du dx is currently being multiplied by your core function, life is good. You'll be able to do chain rule immediately. If du dx is almost in there, but it's missing a coefficient, you would multiply the inside by the missing coefficient and place the inverse outside of the integrand. And I'll show you how to do that because that's a lot of words. If you cannot get the du dx, then you're just kind of stuck and you'd have to use some other technique. The next step is you replace all of your expressions with u's and du's. And so you get rid of all of the x's in your starting thing and you turn everything into u's. And after you've done that, where you've turned everything into u's, you can substitute back to get back into x's. Here is a practice problem, which is all worked out here, but let's start and just see if we can show all of these steps with this particular example. So the integral of sine of 2x e to the cosine of 2x dx. So first things first, let's break this function apart as much as we possibly can. And so looking at this, we have the product of two things. One of them is a sine with a 2x on the inside. The other one is an exponential, which has a cosine of 3x on the inside. So this is the composition of two functions. This is the composition of three functions. Looking at this, if I were to try and identify what the core function is, what the function is which has the most stuff inside of it, I would say it's going to be this e to the stuff function, e to the cosine of 2x. And so I would let u be the stuff which is inside of that. And so I would let u be equal to cosine of 2x. if u is equal to the cosine of 2x, then that would mean that our du dx is going to be equal to, well, cosine would go to negative sine of 2x, and then we would need to multiply by a 2. Looking at our function and breaking it all apart, we could see that this is an e to the u. Now the question is this bit out in front that's being multiplied equal to negative 2 sine of 2x? And it almost is. What's missing is a negative 2. And so what we can do is we can put a negative 2 in there as long as we balance it out. And the way we balance it is we'd multiply by negative 1/2. Because if you remember, negative 1/2 times negative 2, they just cancel out. And if it cancels out, you're all good. Well, now looking at this, we have that this term is e to the u. And this term over here is du dx. Well, if we have du dx times dx, we can kind of think of those dx's as canceling. It's a little bit more complicated than that, but the math will check out. And so when we rewrite this, our negative 1/2 is going to stay there. And then we can rewrite this in terms of u's. And so this would be e to the u. And if you wanted to, you could say it's du dx dx. But as I was saying, when we see it written this way, it might be easier to just view this as e to the u du. And this is something which we can integrate without any problems at all. And so integrating that, we get negative 1/2. Well, the integral of e to the u is e to the u. And then as our final step, we have to remember to replace our u. And so our u was cosine of 2x. And so we would get a final answer of negative 1/2 e to the cosine of 2x plus c. And that's our answer. Knowing me, I got it wrong in the notes, but let's see. I ended up getting a negative 1/2 e to the cosine of 2x plus c. Good. And so it looks like I got it right in the notes. That's always a good sign. So the way I did it in the notes, I said let u equal cosine of 2x, then du dx is negative 2 sine of 2x. And we were missing that component, that negative 2. And so we put the negative 2 inside the integrand, and then we multiplied by a negative 1/2 to cancel it out. After we did that, this term, this negative 2 sine of 2x, it kind of goes away. And a lot of people freak out because it disappears. It's not really disappearing. This negative 2 sine of 2x is really just becoming this du. Because remember, this component is du dx. And so when combined with dx, we get the du. And then we can integrate straight away. I have a number of practice problems here. I don't know that I want to do all of them, especially this first one. The first one looks kind of silly. But let's work through a number of these, and then we'll move on to the next technique. So let's start with this 3x squared e to the 2x cubed. And so the integral of 3x squared e to the 2x cubed. So when we look at this one, what we want to do is we want to again ask the question of what are the functions which are involved? And looking at this, we can see that we have a 3x squared. We have an e to the 2x cubed. So the question is, what is our interior function? And so our main function would be this e to the stuff, and the interior function would be that 2x cubed. the derivative of 2x cubed, du dx, would be 6x squared. And the question becomes, do we have a 6x squared? Well, we don't. We have a 3x squared. What we're missing is a factor of 2. And so we could multiply by 2, as long as we balance it with a 1/2. Now rewriting this in terms of u, we would have 1/2 the integral. The 6x squared becomes our du, and then we're going to have e to the u. So this one looks very similar to that last one we did. That gives us a 1/2 e to the u plus c, which gives us a 1/2 e to the 2x cubed plus c. Let's try another one. Next one we'll do, let's do, this one looks tricky. Let's do this one instead then. Let's do the easier ones before we get to the tricky ones, because some of these can get very tricky looking. And so the integral of x cubed x to the 4th minus 3 dx. Now with this one, we could just distribute the x cubed to the x to the 4th, the x cubed to the 3, and then integrate both of those terms, and it will work just fine. But if we wanted to, we could instead say that u is equal to x to the 4th minus 3. Our du dx then would be equal to 1/4 of x cubed. Well, we're missing that, or sorry, I'm skipping ahead, 4x cubed. Like I mentioned before, a couple of sessions ago, you're going to get your derivatives and integrals mixed up all the time. And it's just going to be one of those things that you're going to have to practice with. And so we need that 4 in here. And so to balance it, we need a 1/4. Well, this becomes our du dx. This is just u. And so we could say that this is 1/4 of the integral of u du, which would be 1/4 of 1/2 of u squared plus c. And that gives us a 1/8 of u, which is x to the 4th minus 3 squared plus c. 1/8 u squared plus c. Now, if you were to have distributed, it might have been a much easier approach. But this is just showing that this is a technique which you can use in various situations. The next one is one where it might be a little bit trickier. And often with these, you're just going to have to play around with them to see which techniques work and which ones don't. And so our next one is going to be the integral of 1/x natural log of x. And so looking at this, it might not be apparent that you have an interior function, or figuring out what the interior function is might itself be kind of tricky, because we have 1 divided by x times the natural log of x. What might help is to instead think of this as the product of 2 functions. In this case, this would be the product of 1/x times 1 over the natural log of x. And the reason why it might be nicer to see it that way is because then we can see that this function here has a natural log of x inside of a 1 over x function. And so if we let u be equal to the natural log of x, well then du dx is going to be equal to 1 over x. And notice we actually have a 1 over x there. And so we have our du, and then this is our u. And so we can rewrite this as the integral of 1 over u du. And we know what the integral of 1 over u is. It's going to be our natural log. And so we would get the natural log of the absolute value of u plus c. And then our last step is to substitute back in our u. And so we would get the natural log of the absolute value of the natural log of x plus c. Notice before we did not have a way of doing an integral which involved a natural log. Now we do. And so that's something that we want to keep in mind. We have now expanded our tool set to include functions which we did not have the formula for before. But these things can get complicated. And so here is one which is lengthy and a little gross. The square root of e to the 2x minus x squared times e to the 2x minus x. That is a very complicated looking function. And hopefully you all agree that that's kind of a complicated function. We can still do this substitution method though. And so we want to look for functions inside of functions. And when we look at the left side, well, this has an e to the 2x minus x squared within a square root function. And so if we let u be that interior function, e to the 2x minus x squared, then our du dx is going to be equal to 2e to the 2x minus 2x. And we almost have that here. The only thing we're missing is a factor of 2. And so we can put a 2 in there as long as we balance it out with a 1/2. And now this long integral is going to become 1/2 the integral of the square root of u du. Much simpler. From here, we can integrate like before. So the integral of square root of u, well, this is u to the 1/2. So it would become u to the 3/2. And then we need to multiply it by 2/3 to balance it out. The 2's would cancel, leaving a 1/3. And then the u is e to the 2x minus x squared to the 3/2. And so these things, they can get messy. Sometimes it's not clear what you're supposed to integrate, or sorry, what your u value is supposed to be. But you just have to play with it a bit, and eventually it should all fall together. So here's another example. The integral of 1 over 3x minus x squared, x cubed minus natural log of x squared. So again, the question might be, which function has the interior function? And well, looking at this, we have this thing times this thing, which is squared. And so we might try our u to be the interior function, x cubed minus natural log of x. The derivative of that, du dx, is going to be equal to 3x squared minus 1 over x. And now looking at this, we almost have that. The signs are both wrong. And so that's one challenge. But we also have that it's off by a factor of 3. And so we would need to multiply by a negative 3, which means we would need to balance it with a negative 1/3. So after all of that labor, we get that this is equal to negative 1/3. The integral, this becomes our du. That is going to be u squared. Which gives negative 1/3. The integral of u squared is going to go to a u cubed with another factor of 1/3. Which gives negative 1/9. And then it's going to be u, which is x cubed minus ln of x. And that is going to be to the third. The next one's interesting because it is going to be a definite integral. And we haven't done any definite integrals yet. And definite integrals are a little bit trickier. There's actually 2 techniques for doing these. And I'll see if I can remember both techniques and show you. And so our first one is going to be this one. Let's rewrite the problem first. 0 to 5 of t square root of 25 minus t squared. And so when we see this 0 to 5, one thing we can do is we can just ignore that problem or that part of the problem until the end. And that is a viable way of doing this. It's the way that I did it for many, many years, to be honest with you. And so in this case, we can do the same substitution stuff we've done in the past. And so we can see that this is a function inside of a function. Our u would be 25 minus t squared. And so our du dx would be equal to negative 2t. Well, we are missing that negative 2. So we can put the negative 2 in, which means we would need to balance it with a negative 1/2. And we can balance that. And so now when we integrate this, we're going to get a negative 1/2 going to be that this is our our du. So it'll be the integral of the square root of u. And notice what I did here is I just dropped the 0 and the 5. I said, I know I'm going to have to deal with it later, but I don't have to deal with it now. And so you can do the entire problem, get it back into t's, and then plug the 0 and 5 in. And so integrating this now, we have the negative 1/2, and then it's going to be a u to the 3/2, but then we're going to need to multiply by a 2/3, which we've done before. And then we'll put the line here because we know we're going to need to evaluate it. Turning this back into t's, we would get negative 1/3. The u becomes 25 minus t squared to the 3/2. And now that it's back in terms of t's, we can evaluate this. And so this would be from 0 to 5. So basically, whenever we were dealing with u's, we just kind of ignored the bounds. But now that it's back in terms of t, we can plug those bounds back in. And that means we can do the fundamental theorem of calculus. And so we would get negative 1/3. Then it's going to be 25 minus 5 squared is 25 to the 3/2 minus a negative 1/3. 25 minus 0 to the 3/2. Well, this is 25 minus 25 is 0, so this term goes away. The minus cancel, and then 25 to the 3/2 would be 125. And so we end up getting 125 over 3. This is a good technique. It's not the technique you will typically see in textbooks, though, because there is a shorter approach. And so let's see the shorter approach for this problem. So we'll do the exact same problem, 0 to 5 of t square root 25 minus t squared. And the problem starts out in much the same way. And so we will start by figuring out what our u is. And so our u is going to be 25 minus t squared. Our du dx is going to be negative 2t. And so we know we're going to need our negative 2 in here. We know we're going to need our negative 1/2 to balance it. And so we can rewrite that. And we would rewrite that as the integral, sorry, the negative 1/2, the integral of square root of u du. Here's where the second technique differs. Since we know the bounds in terms of t are 0 and 5, we can actually plug that into this function u, because technically this u is a function of t. And so we could think of this as u of t. And, oh, I wrote du dx. That's bad. This is du dt. Same with that one. Shame on me. And so since this is a function of t, we could say, what is u of 0? Well, if you plug 0 into this function, you're going to get 25 minus 0, which is 25. If you plug in 5, you get 25 minus 25, which is 0. And so our lower bound, which was 0, is now going to become 25. Our upper bound, which was 5, is now going to become 0. And now we don't have to turn it back into t's. So we can just continue with this integral. And so we would get that this is now equal to the negative 1/2 times 2/3 u to the 3/2. But now we actually know what we're evaluating it at. It'll be going from 25 to 0. Again, the 2's cancel out, so we have negative 1/3 of 0 to the 3/2 minus negative 1/3 of 25 to the 3/2. And again, doing the math, we get 0. And this is going to be 125 thirds. Either of these techniques works. And so if you ever see a definite integral, you can either carry it all the way through and turn it back into t's and then evaluate it, or you can do this trick where you actually figure out what the new bounds would be for your u variable. Either way works. I used this first way for a very, very long time, longer than I probably should have, because you don't really have to think about it that much. but this technique is definitely the way which is taught in the textbooks, and it's the preferred way to do it. And so it might be a good idea to get comfy with that approach. Let's see, we've got a few more here. Most of them are pretty much the same, though they can get fairly lengthy. Let's do this one, though. The integral of tangent. Now, I mentioned at the beginning of today that we don't have a formula for that one. We haven't learned a formula for that one. And so let's create a formula for this one. The integral of tangent, we can think of as the integral of sine over cosine. And this we can do a u substitution with. If we let u be equal to cosine of x, then our du dx is going to be equal to negative sine. Well, we have a sine, we're just missing that minus. And so we can rewrite this as the integral, or negative integral, of 1 over u du. And 1 over u is one which we can integrate. And so we end up getting that this is negative the natural log of the absolute value of u plus c. And then our u we can substitute back in, and we get that it is equal to the negative natural log of cosine of x. And hopefully you find that kind of interesting, because when we look at this, we started with a tangent, and we're saying that the area under the curve of tangent can be figured out by taking a natural log of the cosine. And that's something which is kind of interesting, because you don't usually think of natural logs as being associated with tangents, but here they're clearly very closely related. We can do something similar with cotangent, and we can actually do something similar with secant, but with secant, it's a little bit trickier. And so let's see how we would do that. Let's say the integral of secant of x, and we're going to rewrite this as secant squared, or sorry, the integral of secant squared of x plus secant x tangent x over secant x plus tangent x. I would not expect you to be able to come up with this idea. This is a really cool trick, but it's not something which is very common. It is something which can be done, though. And so looking at this, if you factored out a secant from the numerator, you would see that there's a secant x plus tangent x, and that would cancel with the denominator. Well, notice now that we could let u be that denominator. Secant x plus tangent x. Then your du dx is going to become secant squared, or sorry, secant x tan x plus secant squared of x. And that secant x tan x plus secant squared x is precisely what you have in your numerator, which means that we can now rewrite this as the integral 1 over u du, which we know is going to give us a natural log, absolute value of u, and we can then plug our u back in. Natural log, absolute value, secant of x plus tangent of x. So again, I find that kind of interesting. We started with a secant, and remember, secant is 1 over the cosine. Doesn't seem to have anything to do with exponentials or logarithms. But when we are trying to find the area under the curve, or just the antiderivative, we end up getting this natural log that pops out. These functions that we've been playing with are much more closely related than we might have thought in the past. Our trigonometric functions and exponential functions end up being extremely closely related to one another in very, very interesting and weird ways. And we'll be playing with that the rest of the semester. And so that was our first technique of 4, the substitution method. We did a lot of examples, and the reason we did a lot of examples is because I think that you could use as much practice and as many examples to look back to as possible. But we do have a few other techniques to get through. And so let's see if we can go through them. The next one is integration by parts. So we just did the chain rule backwards. Integration by parts is the product rule backwards. And let's see if we can see how that is. I kind of have it written here, and so maybe we'll just read through it. And so recall the product rule says that d dx of u times v is equal to u prime v plus u v prime. Well, we could integrate both sides of this if we wanted to. And if we did, well, the integral of a derivative is just going to give you the uv, give or take a constant c. And so there should be a plus c somewhere in here. But then when we do the right side, well, u prime is du dx. And so this would be v times du dx. And this one would be u times dv dx. Well, we can't really do much with it. And so when we integrate, we're just going to get the integral of v du dx plus the integral of u dv dx. This might not look great because now we have 2 integrals in here. But notice that we could solve for one of those integrals. And when we do, we get this formula. They also cleaned it up by canceling out some of those x's. But this formula is the integration by parts formula. And I'll write that down real quick. Integration by parts. It is that the integral of u dv is equal to u times v minus the integral of v du. And technically, the dv is really dv dx. And then the du is really du dx times dx for each of them. But this gives us a way of taking one integral and rewriting it as a different integral. And that different integral might be something which is easier to integrate. And so to solve an integration, or to solve an integral using integration by parts, what you want to do is you want to look at the different components in your integrand to identify what the core functions are that you're dealing with, and which ones are easier to differentiate and integrate. Choose your u value to be an expression that you can differentiate and dv dx to be one which you can integrate. Then find du dx and v. Plug your values from dv dx, u, du dx, and v into this formula. And then just solve whatever remains. And you just keep doing this until you get your final answer. I have an example here. Yeah, I guess we can do something similar to this. I want to do one which is a little bit harder than this one. And so let's do the integral of x e to the 3x. That's a better problem. At least a little bit more complicated. And so the integral of x e to the 3x dx. Notice with this one, we have the product of 2 functions. What we're going to want to do is we're going to want to take the derivative of one of these functions, and we're going to want to take the integral of the other one. Because in our formula, we have a u and we have a dv. And so one of them is going to be our u. That'll be the one we take the derivative of. And one of them will be our dv. That'll be the one that we take the integral of. And so in this case, I would probably let our u be equal to x. And then our dv, or if it helps you, dv dx, is equal to e to the 3x. The reason I chose our u to be the x value is because when we take the derivative of u, we would get du dx is just equal to 1. Our v value, well, to get v, we would have to take the integral of e to the 3x. And we can take the integral of e to the 3x. It's not as easy as taking the derivative, but it's not that much harder. We get a 1/3 e to the 3x. And now we have our 4 components. We have our u, our du, our v, and our dv. We can plug it into this formula. So plugging it into this formula, we would get that this is equal to u times v. So u times v is going to be 1/3. Actually, I guess I'll just write it straight away without trying to simplify it first. It would be u, which is x, times v, which is 1/3 e to the 3x, minus the integral of v times du, 1/3 e to the 3x times 1 dx. And this part cleans up very nicely. You can just pull the 1/3 out and we'll get something nice. 1/3 x e to the 3x minus this thing is something which is very easy to integrate because this 1 doesn't really do anything. And then the 1/3 you could factor out if you wanted to. The integral of e to the 3x is 1/3 e to the 3x. And so we're going to get another factor of 1/3 out of this, giving you a 1/9 e to the 3x plus c. And that's the idea behind integration by parts. And so with integration by parts, we started with the product of 2 functions, and our substitution didn't work very well. You could try and do a substitution. It ain't going to do it here. When you take the, or when you find all of the components, we start with one of them as being u, and the other one as being our dv. We then have to find our du dx and our v. Once we have those, we can plug them into this formula. The integral of u dv is equal to uv minus the integral of v du. And it's really just plugging them in. And so our u times v minus the integral of v times du. Once they're in there, you have a new integral, and hopefully that new integral is easier than the one you had. If it is not easier, maybe you chose your u and dv incorrectly, in which case just choose the other one to be u and try it. The nice thing is this will work no matter what. You might not get to an answer that is nice. You might always have this integral carried along, but as long as you can keep integrating and differentiating, you're good to go. Sometimes you have to do this process multiple times, and that can be a little bit tedious. Again, these problems don't look great, those first 2 at least. So let's try a different one. And so let's try and combine those first 2, and we will do the integral of, I want to do x squared sine of pi x dx. And so with this one, we can do the same process. We have 2 functions. One of them we're going to be taking the derivative of. The other one we're going to be taking the integral of. Whether we're taking the derivative or the integral of the sine function does not matter, because it goes back and forth between sine and cosine. X squared, if we integrate it, it goes to x cubed, which is worse. And so we're going to want to take the derivative of x squared. which means that we are going to let that be our u. And so now we have our u is x squared. We have our dv is sine of pi x. We have our du dx, which is 2x. We have our v, which would be, that's going to be a negative 1 over pi cosine of pi x. Not very nice, but still manageable. And so now we can integrate this using our integration by parts. Starts with u times v, which, simplifying this, gives a negative 1 over pi x squared cosine of pi x. So that's u times v, minus the integral of v times du. Well, we could take our minus sign and then a 2 over pi, then an x cosine of pi x. Now the question becomes, did we make this nicer or worse than what we started with? And it's definitely more complicated, but the integral is actually an easier integral. For one, we can distribute this and make that a plus plus, but we're going to have 2 over pi times x cosine of pi x. The fact that this exponent decreased by 1 means that this is now something a little bit easier. And so let's repeat the process. And so we're going to let this be u, and this be our dv. This term is just going to hang out the entire way through now. But we can repeat this process by doing integration by parts for this term. And so u is 2 over pi times x. dv dx is going to be equal to cosine of pi x. R du dx is now equal to 2 over pi. And our v is now going to be equal to 1 over pi sine of pi x. And so let's rewrite this now. And so this is equal to, this first term, like I said, is just going to hang out. So it's going to be the negative 1 over pi x squared cosine of pi x plus, now it's our integration by parts. U times v would give a 2 over pi squared x sine of pi x minus the integral of v du, which is 2 over pi squared sine of pi x. And again, ask the question, is that better? And it very much is, because this term we can actually take the derivative of straight away. And so that's going to give us our final answer. It's going to be negative 1 over pi x squared cosine of pi x plus 2 over pi squared x sine of pi x. And then integrating this, well, the integral of sine is going to go to a negative cosine. So we're going to get another negative out of this. And so a negative and a negative gives a positive again. And so we then get a plus 2 over pi to the third, because we get another pi coming out, cosine of pi x. plus c. Integration by parts problems can get tedious because you might have to do this over and over and over again. Like, what if this had been an x to the 7th instead? We could do it, but we would just be doing a lot of repetitive actions throughout the entire problem. And so ideally, we'd like to avoid that. Let's use this technique now to figure out how we can do the natural log function. And so the integral of the natural log. We can use integration by parts to do this problem. And I know what you're thinking, we don't have the product of two things, so how can we do integration by parts? Well, the way we can do it is we can use the identity property of multiplication. You remember from the identity property of multiplication, there's always an imaginary 1 in the mix. And so now looking at this, we have the product of two functions. It's just one of those functions is just 1. We do not have a way of integrating natural log of x directly, and so we better be taking the derivative of it. And so we will let this ln of x be our u value, and then our 1 is going to be our dv. And so we can now say that u is natural log of x. Our dv dx is 1. Our du dx is then 1 over x, and our v is going to be x. Using the integration by parts, we can then say that this is equal to u times v minus the integral of v du. But notice what happens here. The x and the 1 over x cancel. And so this is really just the integral of 1. And the integral of 1 is just x. So that is the formula for the antiderivative of the natural log of x. It's kind of a fun thing because, again, much like when we were dealing with the tangent, we didn't have a formula for it, but using our techniques, we were able to develop a formula for it. Same goes for natural log. And we can do this with any functions that involve the natural log. Let's do one more just for good measure. How about x to the 5th natural log of x? The integral of x to the 5th natural log of x dx. And so when we look at this function, again, we might try and figure out which one we want to take the derivative of and which one we want to take the integral of. I would recommend taking the derivative of our natural log of x, because if we took the integral, we'd have to be playing with this function everywhere, and that does not sound very fun. So let's let this be our u. This will be our dv. Well, then u is natural log of x. dv is x to the 5th. Our let's say dv dx. Our du dx is going to be 1 over x, and our v is going to be 1/6 x to the 6th. Crunching the numbers, we get that this is equal to u times v. So 1/6 x to the 6th natural log of x minus the integral of v du. Multiplying those, you get 1/6 x to the 5th, because x to the 6th divided by x cancels. And this we can integrate. We will get another factor of 6 that comes out of it. So we'll get 1/6 x to the 6th natural log of x minus 1/36 x to the 6th plus c. So that's the integration by parts technique. If you ever have the product of two objects and it looks like one of them is not the derivative of the interior of the other one, then this is probably going to be the technique to go to. If you want a couple of harder problems, I have a couple of harder problems here. I won't work through them because I might need an extra whiteboard. And so e to the x cosine of x, and then sine squared of x. You can find those online if you'd like. But that leads to the next technique, which your book has an entire section devoted to, and I don't know how I feel about that. It's the idea of using tables of integrals. And so if you look in your textbook, in the back of the book, there is a table of integrals, which gives you the formulas for a bunch of different hard to integrate integrals. And that's what section 5.7 is all about in your textbook. It's just about trying to understand how you can integrate things like that. Be aware, not everything can be integrated. We already talked about that. But if you are trying to integrate using a table of integrals, that means that you're trying to do it in the real world and you're just trying to find the answer. If you're just trying to find the answer, just go to Wolfram Alpha. Wolfram Alpha is a very good tool for doing that type of stuff. And let me see if I can pull it up real quick. Here's our good friend Wolfram Alpha. Let's say we want to find the integral of, how about sine squared of x dx. So the integral of sine squared of x dx is equal to 1/2 of x minus sine of x cosine of x plus a constant. That's Wolfram Alpha. Wolfram Alpha is the tool which mathematicians use when they are doing computations, because it'll tell you that, and then it'll give alternative forms, it'll give you some graphs, and it'll tell you just about anything that you want to know about this. And so there's a lot of additional nice tools. Like here it is from 0 to pi. It tells you that it's pi over 2. I wasn't asking that, but it's great to know that that's the answer. And this will work for just about anything. There are some, though, which it'll struggle with. And let's see if I can find one of those. I wonder about natural log. And so if you do natural log, notice that it says the integral of log of x dx is equal to x log of x minus 1 plus constant. Notice that when you see log x generally refers to the common log and not the natural log. Wolfram Alpha refers to log as the natural log, which is different from mathematics. That's because it was developed by computer engineers. And so if you were to write the answer for the integral of natural log of x as x log of x minus 1, that would be incorrect. Wolfram Alpha struggles with logarithms. Pretty much all computer algebra systems have some issues like that, where there's formatting which is just a little bit off. For instance, photomath. Photomath is a common one used by students. It does U substitutions weird, I seem to recall. It can do them, it can get you an answer, but in getting you the answer, it will use a different letter besides U, and it may give you some very weird looking answers. And so, again, be very, very careful when you're dealing with stuff like that, because the answers that you get may not follow from whatever your work might be. And sometimes, if you were getting an answer which has log, if you were to write log, you'd be in trouble, because your computations would be way, way off if you ever had to plug them in. And so do be aware that technology does have its limitations. But that's our third technique. And so our second technique was integration by parts. Our third technique was the table of integrals. Our next technique is partial fraction decomposition and long division of polynomials. This is a very, very complicated technique, and the problems related to it can get very long and very tedious. the idea behind it is if we think back to Algebra 1 and Algebra 2, we had long division of polynomials. And so if we saw something like x cubed plus x over x minus 1, we could do long division and get it rewritten as x squared plus x plus 2 over x minus 1. Well, this second term is much, much, much easier to integrate than this first term. And so if we do this long division, we will get something which is much easier to integrate. Partial fraction decomposition, I'm guessing many of you have not seen. This is a pre-calculus idea, and it's kind of an extension on long division. Partial fraction decomposition is a way of rewriting something like this as the sum of the factors of your denominator. And so if you look at this denominator here, 2x cubed plus 3x squared minus 2x, that can be factored to a 2x, a 2x minus 1, and an x plus 2. Or maybe it's just an x, a 2x minus 1, and an x plus 2. That's what 2x cubed plus 3x squared minus 2x will factor to. Well, we can figure out what the new coefficients are for those terms. And once we do that, we can get something which is easier to integrate. This second term is just going to be a bunch of natural logs. And it's almost always just going to become a bunch of natural logs. And we can integrate natural log, or we can get natural logs fairly painlessly. To get there is much trickier. And here's the general strategy. I don't think I gave problems where you would need to use all of these terms, but let's walk through it real quick. And so to solve an integral using partial fraction decomposition, step 1 is use long division to simplify the rational expression, if possible. Then you want to factor the denominator. Step 3 is the doozy. Set your rational expression equal to a set of simpler rational expressions using the factors of your denominator as follows. And so for each factor of the form x plus r, where r is just some number, create a term of the form a over x plus r. For each factor of the form x plus r to the n, where there's an exponent on it, create a set of rational expressions of the form a over x plus r plus b over x plus r squared plus c over x plus r cubed, all of the way out to x plus r to the n. And then if you have terms which cannot be written as a linear term and are stuck as a quadratic term, we have something for that too. And that can get just very, very messy. From there, your goal is going to be to figure out what your coefficients actually are. So what the A, B, and C and all of those letters are actually going to be. And once you've figured that out, we can then integrate. Note, we're mostly going to focus on the 3A case. We're going to make it so that we're dealing with the easiest cases. And I believe your book does that, and I think the homework does that as well. I don't think we have any of the monstrous problems. But here's an example of one which is fully worked out, and this is one which has 3 variables. I might start out with one which just has 2 variables. And so we'll keep this one here in the notes. I'll just come up with one real quick. Yeah, I don't like these. And so let's try a different problem. Let's say that we have the integral of 2x minus 7 over x squared minus 5x plus 6 dx. And so looking at this, it's not a very nice thing to integrate. We could try and do a, what's it called? A U substitution. It's not going to work great. And so we might want to just try this partial fraction decomposition. Looking at our denominator, the denominator factors very nicely. And so looking at our denominator, we know that we can rewrite this as the integral of something over x minus 2 plus something over x minus 3. because we know that x minus 2 times x minus 3 is x squared minus 5x plus 6. Well, we don't know what these two values are. And so what we're going to do for now is we're just going to call them a and b. And now we're just going to ignore all of our integration, and we're just going to go back to our good old friend algebra and see if we can figure out what a and b are. So looking at this, we would start out with 2x minus 7 over our x minus 2, x minus 3 is equal to a over x minus 2 plus b over x minus 3. If we multiply everything by the common denominator, then we'll get rid of all of our denominators. And so our common denominator in this case is going to be the x minus 2, x minus 3. And so we're going to multiply everything by x minus 2, x minus 3, x minus 2, x minus 3, and x minus 2, x minus 3. On the left side, it all cancels. We're left with 2x minus 7. On the right side, well, for this first term, our x minus 2 cancels. And so that would leave us with a times x minus 3. And then for the last one, our x minus 3's cancel, which leaves us with a plus b times x minus 2. Cleaning this up, we get 2x minus 7 is equal to ax minus 3a plus bx minus 2b. Now here's where we get a few different techniques. One technique, which is a very common technique, is to just plug values in for x. And so you can plug 0 in for x and you'll get something, or you can plug 1 in for x and you'll get something. And that's a very good way of doing it. It's not the way that I typically do it though. The way that I would typically do it is I would say this has to work regardless of what x is. And so we can kind of break apart our x terms and our non-x terms. And so if we just look at our x terms, we have our x terms have 2x is equal to, maybe I'll even space this out a little bit. And so 2x needs to be equal to ax plus bx. For our non-x terms, just our number terms, we have -7 is equal to -3a minus 2b. And now hopefully all the algebra folks in the room recognize that this is 2 equations and 2 unknowns. And since we have 2 equations and 2 unknowns, we can solve it. The way we would do it is we would multiply top one by 2, and then we could add the 2 together. And so that would give us a 4 equals 2a plus 2b, and a -7 equals -3a minus 2b. Adding them together, we get 4 minus 7 is -3. My numbers aren't working today. 2a minus 3a is going to give a -a, and then our b's cancel out. So that tells us that a is equal to 3. We could do the same thing to figure out what our b value is, or we could substitute the 3 back in and get it either way. substituting might actually be easier, since if we substitute into this first equation, we would say that 2 is equal to 3 plus b, which tells us that b is equal to -1. And so we did that entire algebra process so that we could figure out what a and b are. And now we know that a is 3 and b is -1. And so now we can rewrite this as this. And this is easy to integrate, because the integral of 3 over x minus 2 is going to be 3 natural log absolute value x minus 2. The integral of -1 over x plus 3 is -1 times the natural log of absolute value of x minus 3 plus c. With partial fraction decomposition, the calculus part is excruciatingly easy. The algebra part is excruciatingly painful. And this one, as you saw, became a 2x2, 2 equations and 2 unknowns. The one which I had in the notes, so sharing the screen again, worked out, was a 3x3, but it was the exact same process. And so if we have x squared plus 4x plus 1 over x minus 1, x plus 1, x plus 3, we can rewrite this as a over x minus 1 plus b over x plus 1 plus c over x plus 3. And then you just have to figure out what a, b, and c are. And it's a gross algebraic process. It's completely doable. And eventually you get a, b, and c. Once you have your a, b, and c values, you can just plug them into this and integrate, and you're done. But getting those a, b, and c values, that is what takes a little bit of time. I do have a few extra problems here. Honestly, if you would like to see more problems, I would probably recommend just going to YouTube and typing in partial fraction decomposition and getting an extra video, because these problems, they're very, very tedious, but it's just the algebra that is tedious. And so if you need the practice with the algebra, I might just do the quick search on YouTube. Just do a search for partial fraction decomposition. You'll get hundreds of videos. And instead, let's go on to our final technique, improper integrals. So improper integrals are integrals which involve infinity. And so there are some integrals that you're going to be seeing, some definite integrals, which either go to an asymptote or they have infinity as one of their bounds. If you have infinity as one of your bounds, what you need to do is you need to rewrite it as a limit. And I have a couple of them worked out here. And so this first one is the integral from 1 to infinity of 1 over x squared. Well, since we can't really plug infinity in, infinity isn't a number, it's a limit itself. What we would do is we would rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x squared. And then we would just integrate like normal. So the integral of 1 over x squared is -1 over x from 1 to b. And then when we evaluate it, we would get the limit as b goes to infinity of -1 over b minus -1 over 1. And then as b goes to infinity, well, this would become -1 over infinity. -1 over infinity. Yeah, -1 over infinity, which goes to 0, because 1 over a really big number goes to 0. And then minus a negative would become plus, and 1 over 1 is 1. So we get 0 plus 1 is 1. There's also the case where the value itself might be undefined. And so, for instance, with this one, the integral from 0 to 9 of 1 over the square root of x, at 0, square root of 0 is 0, and this gives 1 over 0, so it's undefined. That doesn't mean we can't solve it, though. And so in this case, we can actually find the area under this infinite region. The way we would do it, exactly the same. And so say limit as a goes to 0, the integral from a to 9 of 1 over square root of x dx. We can integrate that, and that'll give us limit as a goes to 0 of 2 square root of x from a to 9. And then we can plug in the values. And so it'd be 2 root 9 minus 2 root a as a goes to 0. Well, 2 root 9 is 6. And when you plug 0 in, we get 0. So our answer is just 6. I have a note here saying that if you want, you can shortcut it and not put the limits in there, but it's mathematically better to include those limits. Also, sometimes the solutions will converge to a nice value, but more often it's not going to. It'll just diverge. So if you think about the integral from 1 to infinity of 1 over x dx, well, that one does not work out so well. You actually get infinity out of that one. And here I have mixed practice. These 3 problems are based on all of the stuff that we've done up to this point today. And so this first one, the integral from 0 to infinity of x e to the negative x, you would have to use your integration by parts in order to solve this one. The next one, integral from 0 to infinity of x e to the negative x squared, well, that's going to be a u substitution problem. And then this last one, the integral from 2 to infinity of 1 over x squared minus 1, that's going to be a partial fraction decomposition problem. And so these 3 are good to practice with. And let's see if we can do them. We'll start with number 1. The integral from 0 to infinity of x e to the negative x dx. And so again, we should rewrite this. We should say that this is the limit as b goes to infinity of the integral from 0 to b of x e to the negative x dx. And then we want to try and figure out which technique we need to use. In this case, we have the product of 2 things. There really isn't an interior function though, and so that tells us that we probably want to use integration by parts. If we let u be our x and our e to the negative x be our dv, then we would get u is equal to x. Our dv dx is e to the negative x. Our du dx is equal to 1. And our v is going to be equal to negative e to the negative x. And so we can now rewrite this starting integral as the limit as b goes to infinity of u times v. So u times v is x, I guess we could say negative x e to the negative x. And this would now be evaluated from 0 to b minus the integral of v du, which is going to be a negative e to the negative x times 1. And this would be from 0 to b. Well, let's just clean up this final integral real quick. Our limit as b goes to infinity of negative x e to the negative x from 0 to b plus integral of e to the negative x is negative e to the negative x. And this is going to be from 0 to b. And looking at this, we might have a case where we're going to get something undefined. But let's see. And so we now have limit as b goes to infinity of, oh, maybe not. And so this is going to be negative b e to the negative b minus, at 0, it would be a negative 0 e to the negative 0 minus, for this one, it's going to be an e to the negative b. And then it's going to be minus a negative e to the negative 0. And so we have 4 terms and we have 4 limits. Our first one, negative b e to the negative b as b goes to infinity. Well, as b goes to infinity, it's going to become infinity times a 0. And this e to the negative b is going to go so much faster than this one. And so this term is going to go to 0. This term is also going to be 0. E to the negative infinity is going to also go to 0, which means all we're left with is this last term, plus e to the 0. So all of that was just to get 1. And so the integral from 0 to infinity, the area under the curve of x e to the negative x from 0 out to infinity is just 1. It's kind of an interesting one. The next one's fairly similar, but a little bit easier. And the only thing that it changed is it's now going to be an x e to the negative x squared. And let's see how that changes things. And so with this one, again, the setup is exactly the same, but now instead of doing an integration by parts, we can do a u substitution. If we let u be equal to negative x squared, then our du, or du dx, is going to be equal to negative 2x. We almost have that. We would need to balance it with a negative 1/2. So now we can integrate no problem. And so integrating this, or rewriting this, is now going to be the limit as b goes to infinity of negative 1/2. The integral, that becomes our du dx. This is going to be our e to the u. And if we wanted to, we could change the limits of integration. And so if we were to do, let's see, our 0 value, and so u of 0 is going to be negative 0 squared, which is just 0. And then if we were to plug our b in, well, that's going to give us a negative b squared. So that tells us that we're going from 0 to negative b squared. This should hopefully work. Let's find out. So now we have the limit as b goes to infinity of negative 1/2. It's going to be e to the u from 0 to negative b squared, which gives limit as b goes to infinity of negative 1/2. Then it's going to be e to the negative b squared. And then it'll be minus a negative 1/2 e to the 0. Well, as b goes to infinity, this term goes to 0. Plus e to the 0 is 1. So we end up with 1/2. And so the integral from 0 to infinity, the area under this curve of x e to the negative x squared from 0 out to infinity is just 1/2. Again, that's kind of a fun one. Our last one is the partial fraction decomposition one, which I know is everyone's favorite. And so let's try that one. This is the integral from 2 to infinity of 1 over x squared minus 1. And with this one, again, we're going to want to rewrite it as a limit. And so we'll say the limit as b goes to infinity. And then we'll make it the integral from 2 to b. And then we might as well break this up at this point so that it's a over x plus 1 plus big B over x minus 1. Maybe I'll even do that with a different color because we know that we are going to be replacing them before the end. And now we got to figure out what a and b are. And so we know that 1 over x plus 1, x minus 1 needs to be equal to a over x plus 1 plus b over x minus 1. Well, we can multiply by the common denominator, which is x plus 1, x minus 1. And we'll do that for every single one of these. X plus 1, x minus 1. For the first one, everything cancels, and so we're left with 1. For the next one, the x plus 1 cancels, leaving an x minus 1. For the next one, the x minus 1 cancels, leaving a b times x plus 1. Distributing, that gives us a 1 equals ax minus a plus bx plus b. Looking at our x terms, we don't have any x terms on the left side. On the right side, we would have a plus b. Looking at our number terms, well, we don't have, or we do have a 1 on the left side. Then it's going to be a negative a plus b. A plus b equals 0, and negative a plus b equals 1. Guessing this is going to be like a 1/2 and negative 1/2 situation. You can math it out if you want to. I'll go guess and check. So if b is 1/2, then a needs to be negative 1/2, because negative 1/2 plus 1/2 gives 1. And negative 1/2 plus 1/2 gives 0. And so now that tells us what our a and b values are. So our a value is negative 1/2. And our b value is positive 1/2. So we go through that whole process so that we can now finish this up. Limit as b goes to infinity. It's going to be a negative 1/2 natural log absolute value of x plus 1 plus a 1/2 natural log absolute value of x minus 1 dx, oh, not dx, evaluated from 2 to b. And now we can start plugging stuff in. It's not going to be very nice, I don't think, but that's okay. Limit as b goes to infinity. Honestly, before we do that, it might make sense to clean this up a little bit, because we have natural logs and we have our sum and difference formulas. And so we can rewrite this as the natural log of absolute value of this is going to be an x minus 1. And I'm going to keep the 1/2 on the outside because I don't really want to deal with fractional exponents yet. X minus 1 over x plus 1. That looks good. The reason I did that is because I'm pretty sure when we actually plug b in, we're going to get something interesting happen. And so limit as b goes to infinity now, it's going to be the 1/2 of the natural log of the absolute value of b minus 1 over b plus 1. And then it's going to be minus 1/2 the natural log of 2 minus 1 over 2 plus 1. And looking at this first one, b minus 1 over b plus 1, as b goes to infinity, this is going to become the natural log of 1. And natural log of 1 is 0. So this term goes to 0, which leaves this term. I don't know that I like that minus sign, but we'll go with it. And minus sign might be okay. And so that's going to give us a minus 1/2 natural log of 1/3. And we can drop the absolute values because it's positive 1/3. And that's our answer. The area is going to be negative 1/2 natural log of 1/3. And I guess that's okay, because if we think about what the graph of this function is going to look like, the graph of the function is going to look something like this. And so this negative area is corresponding to the area being underneath the curve, or underneath the x-axis. I was a little worried when I saw that minus sign, but no, the minus sign makes sense. And so that gives us our final answer for that one. And that brings us to the end of today's lesson. Let's go through it real quick and see all the techniques that we saw. And so we started with these problems, which looked a little weird. But then we said we can do the substitution method, which is really just the chain rule backwards. And then we said we can do the integration by parts technique, which is the product rule backwards. And then we said, well, there's the tables of integrals, but if you're going to do tables of integrals, you might as well just go to Wolfram Alpha. And then we had partial fraction decomposition, which is really just a bunch of tedious algebra and a little bit of calculus. And then we ended with improper integrals, which are integrals which involve infinity, definite integrals which involve infinity. And really, they're not much different than the stuff that we were doing when we learned the fundamental theorem. It's just a little bit trickier. And that brings us to the end of today's lesson. And so you have an abundance of homework because I want you to get good at these skills. And these skills require a lot of practice. And so definitely put in the time and get good with this stuff. And on that note, I will let you get to your homework.